Today we're going to be talking about coordinate transformations. We'll first delve into pure translations, and then we'll get into rotations. But first, let's talk about what is a coordinate transformation. We've all seen our Cartesian coordinate frames. Here I've plotted the x-axis in red, y-axis in green, and z-axis in blue. This corresponds to a northeast down coordinate frame that we'll use quite a bit when talking about aircraft. I've also defined this purple point. This point is just a point in the space. And so we can easily see that if we look at this point, it's at about 2.5 in the x direction and about 2 in the y direction. So it's really nice. We can define this point very naturally in this coordinate frame. But it may be that there's other coordinate frames of interest. And so the first thing we're going to do is we're going to translate that coordinate frame. So we can look at different values of x, different values of y, right? Probably should keep it on the screen, and a different value for z. So if we go positive in the down direction, we're moving down. So now we've had something that's purely a translation, meaning that the axes are parallel. So this red axis still points in the same direction as the original red axis. We can also do a variety of rotations. So we could rotate about the z-axis. If I get back to about normal. We could rotate about the y-axis. And we could also rotate about the x-axis. All right, so we can move these things, or we can do them all at the same time. And so now we have a very different coordinate frame. We don't have parallel axes anymore to the original one, and we've done a shift. Now the thing to note here is that the point stayed in the same exact spot. The point is defined as a position in space. Think, where is Chicago? Chicago is not moving, but the coordinate frame that we might describe where it is, we can change all we want. So let's jump into it. We're going to talk about this first for the 2D case, and then we'll jump into looking at the 3D case. So if we come back to the slides, we talk really quickly about some motivation. It's going to be used, transformations are used all over in unmanned systems, but realistically, anything you want to do with the aircraft is going to require some sort of a transformation. We could talk about the wind. We're going to define different coordinate frame from the wind. If you want to know where you're looking, right? So your camera is going to have a coordinate frame aligned with it, and so we'd want to transform that between the camera frame and potentially the body frame, or maybe back to the inertial frame. And again, the aircraft will quite frequently want to know where the aircraft is and where it's pointing in terms of the inertial frame. Now we'll define a whole series of transformations, and each one of these transformations is going to make it easy to define some parameter, whether it be talking about Newton's law, if we're talking about the aircraft attitude, various dynamics and forces. Aerodynamic forces and torques are going to be easier to define in one frame versus another. Same with accelerometers. It's going to be really easy to define our acceleration in terms of our body frame. GPS is one that's going to be great in terms of inertial frame. Anyway, so there's a variety of different frames that we can choose from, and some are just really natural to define our points or vectors that we want to talk about. A brief introduction. We'll actually go into a lot greater detail on each one of these reference frames in a different lecture. But we'll use all 7 of these reference frames throughout the course. The first reference frame is our initial frame. So we talked about our north, east, and down coordinate frame, right? And we saw that. The first transformation we're going to make is pure translation. So we're going to go from the inertial frame to the vehicle frame, and that's just our axes are going to stay parallel, and we're going to just move those axes to be on the body of the aircraft. Then we'll make another transformation. We're going to rotate about the z-axis, and that z-axis will allow us to, when we do that, if we were to look at the top of the aircraft and project the aircraft into the northeast frame, then what we're doing here on getting our vehicle 1 frame is just aligning the projection of the aircraft in that plane to have the x-axis aligned with the body or of the nose of the aircraft. Now to get going into vehicle 2 frame, we're actually going to align the x-axis with the nose of the aircraft. And we'll then take this, we'll rotate, so going from vehicle to one frame to vehicle 2 frame, we're rotating about the j-axis. And then to go from vehicle 2 frame to the actual body frame, we're going to rotate about the I-axis. And once we get into the body frame, we'll see that our y-axis, which we denote with this j, is going to be aligned going out the right wing. The z-axis right here is going to be going out the belly of the aircraft. And then the x-axis, denoted with I, is going to be pointed out the nose of the aircraft. We'll then define 2 additional frames to get us to the wind. So we'll define a stability frame, and then we'll define a wind frame. And what that'll do is tell us what is the wind frame with respect to the aircraft. So that'll help us in terms of defining our aerodynamic, or the effects of our aerodynamics. All right, so now let's just jump into a standard frame. So we have our notation that we're going to describe. So we can just write up a point here. I'm going to call it point P. And this point can be easily described. Well, actually, I'm going to move this over here to make it just a little bit easier. Because we've done a really nice rotation, it's really easy to describe this point in either one of these frames. So if we leave it as such, just with just a plain P, we have not assigned a frame to it. We're going to talk about this frame being frame A, the red is frame A, and the blue is frame B. So when we talk about point being in the A frame, we're going to use this superscript to denote the frame. So we'd say we could define the point in the A frame, and if we come over here and count, we'll just do 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is going to say this is our x-axis and this is our y-axis. So point P in the A frame has a value of x equals to 9. And then we'll do 1, 2, 3. So it's 3 in the y direction. Okay, so we have our point A in that frame. We can also define our point in our B frame. So in this case, and say this is our x and this is our y. In this case, our point, again, it hasn't changed locations, but we can change where our coordinate frame is and the direction of our coordinate frame axes. So in this case, we're going to go up 1 in the x direction, and we'll go back 1 in the y direction. So the important thing to note is that these 2 different representations describe the exact same point. And we're going to just use this superscript in both cases to denote our reference frame. Now, there is a slight difference between a point and a vector. So if I define a vector here, a vector is just a direction and a magnitude. So if we say that a vector here is a direction and a magnitude, where we're just going to use point to define a location. Now, this direction and magnitude, this could be defined as the difference between 2 points, and we'll use that later. So difference between 2 points. So now I've drawn a vector v, and I've drawn it in the A frame. So again, we're using that superscript to denote the frame. I could draw down the same exact vector in the B frame, and it's going to keep its same direction and magnitude. So the thing to notice there is that we've, instead of keeping the, like with a point is a location, we're keeping that at the same exact spot. The vector, we're going to change its, we're going to keep its magnitude and direction, but if we express it in terms of one coordinate frame versus another, we always start at the origin and then move in the direction and magnitude of that vector. So in this case, let's write it out. We'd write that VA here is over 1 in the x direction and up 2 in the y direction. So not too crazy. VB is going to be up 2 in the x direction, and it's going to be -1 in the y direction. Okay, so in this case, we've defined points, and we've also defined the and vectors, and we've also defined the reference frame for which we're expressing those points and vectors. So let's talk about our first type of transform. And this transform is just a pure rotation. So, or pure translation, I should say. So we are going to only deal with a single translation transform where we're taking from the inertial to the vehicle frame. So that'll be our major transform. And the idea here is we have some inertial frame. For us, it's going to be called our northeast down frame. And we want to translate that coordinate frame over to where the aircraft is. So basically the center of gravity of our aircraft. But the big thing to note with pure translations is that the resulting axes are parallel. And we saw that over in the little Ross sim. Okay, so it's fairly simple transform. The thing we have to do with this transform is that we need to define a vector between the two sets of axes. So now I'm going to jump into just a two-dimensional example to make this vector just a little bit easier and the notation easier to write down. So again, let's call this let's call the red our A frame, and we'll call the blue our B frame. What we're going to do is we're going to define this vector. See if I can get there. It's almost a straight line. So we're going to define that vector between the two frames, and we're going to call this vector, it's V, and we're going to use the subscripts to describe the vector. So it's going from A to B. Now, again, this vector right here, you can see that since it's at the origin of frame A, we're going to put an A up there. Okay, we could have described this vector in coordinate frame B. If we'd done that, it's over 2 up 3. So this would be that vector in frame B. But that's not as helpful for us right now. So we have our A and our B frame, and we're going to define that vector. And that really helps us do the transform. So let's write this down. And I'm actually going to switch my notation just a tiny bit. I'm going to call this I and B, just to match what I have in my notes. So we'll say that's I, and this is going to be our inertial to our body defined in our inertial frame. Okay, so, and this I'm actually going to switch out just to make it even a little bit easier, because later we'll talk about our vehicle frame, and we already mentioned it. The vehicle frame is just that pure translation. Okay, so now we're good. Let's define the vector between the two frames. We'll say it's VIV, and it's in frame I. This is just going to be, well, this is the vector from frame I to frame V, it expressed in frame expressed in frame I. Okay. And what we're going to do is we're going to use this. We're going to use it to convert from frame V to frame I. We'll say this is our frame V, and we're going to use it to convert to frame I. So in this case, in this example that we've been doing, we now could write out just by looking at this. This is again our X and our Y frame, and we have no rotation, so the X direction and Y direction is going to be the same in terms of both coordinate frames. But we could define VIV in frame I is just going to be equal to, we're going to go over 3 and up 2. So that's not too crazy. So now if I define our point P, we'll define this point right here. We can see that, again, if we looked at P in the V frame, it's at 1 and up 3. If we looked at P in the inertial frame, this one would be over 1, 2, 3, 4, and up 1, 2, 3, 4, 5. So very different values, but they describe the exact same point. Okay, so we have our PV defined. What we want to do, say we know what PV is equal to, then how do we just describe what is PI? So we basically want to form that transform. And here we can just look at it and see, but we'd like a formulaic way of doing that. So what we're going to do is just write down that PI, this relationship, is just simply our VI to V in the I frame plus PV. Okay, so it's as simple as that. So we've not done any rotations. Translations are quite nice. So again, if we take a look at our example, let's double check to make sure it works. All right, so we have our 3 and our 2. We're going to add it to, what do we say, PV was equal to 1, 3. We end up getting a 4, 5, which thankfully was the initial result. Okay, now say that I define another point, just to give us another example. All right, so in this case, this is Q. We'll say that this is equal to -1 in the X direction and up 2 in the Y direction. Again, we could say that Q in the, this is in the vehicle frame. Q in the inertial frame would just be equal to, again, VIV in frame I plus Q in frame V, which would then equal 3, 2 plus -1, 2, which is equal to 2, 4, which if we just take a look at it, over 2, up 4, we're good to go. Okay, so we have that first pure translation, our first transform. One big note to make is that the vectors will not change. So what we've been talking about is purely for points. We want to translate a vector. Well, it's if the axes are parallel, right? So say I define a third element. I'll call this our, oops, make it easy to draw. Let's say this is U. Well, if I go over here to our new frame, U was just equal to over 1 up 3. Again, U is actually going to be equal to over 1 up 3 in the vehicle frame as well as the inertial frame. So pure translations do not change vectors. So that's something to keep in mind. Excellent. So we can look at that vector transform slightly differently, right? So again, we had our u in the I frame, and we have our u, oops, in the V frame. Okay, so we said that our vector is just I just gave you that rule where it's not going to change. But let's just show that fact by noting that ui is just the difference between 2 points. So now if we call this our point P and this is our point Q, well, P in the inertial frame is just over 1 up 3. And Q, in this case, is just 0, 0. So, and that was in the inertial frame. So ui is just going to be equal to pi minus ui, minus qi. In this case, that's pretty easy. It's just going to be pi, 1, 3. Well, we could have looked at the vehicle frame. Oh, and I should have just written this as our vehicle frame. It's still, we can write this generally that u is just equal to p minus q, regardless of frame. So we can just start to use our frame. So let's say we're using vehicle frame, so u in the vehicle frame is going to be equal to P in the vehicle frame minus Q in the vehicle frame. Let's just take a look at this real quick. Our P in the vehicle frame, it's back 2, up 1. And then our Q in the vehicle frame is back 3, down 2. Okay, so let's write that out. So we have minus 2, 1, minus, then we're going to get a minus 3, minus 2. Right? So this minus changes those things to positive, and we get a 1, 3, which is exactly what we expected to get. So we can look at a vector again as just the difference between two points. And another way we could have written this is that UPV here, if we're looking at it in terms of the initial frame, or inertial frame, sorry, would have been V, if we want it in the vehicle frame, but we had it in the inertial frame, we have this V to the inertial, but now we're going to define it in V, plus P inertial, right? And then our Q, V would just be equal to V, our vector from the vehicle to the inertial in the vehicle frame, plus P in the inertial frame. And if we wrote it down, substituting these things in, we have V, VI, V, plus PI, subtract off, then we're going to have V, VI, and V, plus PI. Oops, that should have been a Q. Is obviously equal to now, it's just PI minus QI, right? Because these two cancel out. So we can just see that that vector that defines the translation just cancels out. So it's really nice. So keep that in mind. We have vectors. If we're just doing pure translation, we can simply write it in the either one of the frames. It's going to be the same. We're going to define our second transform as just this pure two-dimensional rotation. So in this case, since it's a pure rotation, the origin of our points are co-located, i.e. they're in the same spot. So again, we're going to have frames A, and we're going to have frame B. Oops, I wrote that backwards. We're going to have frame A, and we're going to say that frame B is blue. Now we need to define what's called our elementary vector. So we're going to say that I sub, and we'll say here this is A. We're going to say this is the unit vector pointing along the B frame, or there I said A frame x-axis. So, and then if I put a B superscript here, I would say described in frame B. So again, the superscript is really important. The superscript tells us which frame it's described in, while we're using the subscript to tell us which frame it corresponds to. Okay, and we have similar things for, we could write up J, we say in the A, B, K, A, B. These are the exact same except for the y-axis, and K is going to be our z-axis. Okay, so let's write these down on this coordinate frame. In this case, for frame A, we would write this as, this vector will be our I, and we'll call it sub A. This vector right here would be our J sub A. Now for our B frame, we'll describe this vector as I sub B, and this vector as J sub B. Now it's important to note, I use the B as a superscript here, but we can write these in either frame. So I, A is just going to be our elementary vector 1, 0. And J, A is going to be equal to our elementary vector 0, 1. Okay, but we could also write this in terms of the B frame like I had mentioned up above. So in this case, we're talking about pure rotations. So we're going to define the angle theta, and we'll say that this angle, to make things nice, is just going to be equal to pi-4 in this example. But that angle is going from our A frame to our B frame. That's going to help us define our translation from our A frame to our B frame. Excellent. So if we take a look at I sub A, right here, we see that it's in the positive direction of I sub B. So in this case, we know that the magnitude, so if we know the magnitude since it's a nice pi-4, right? We actually can define that the magnitude on either one of the axes is going to be square root of 2 over 2. So I A in terms of frame B, right? I'm just going to put the 1/2 out front. And we can see that it's in the positive direction of IB. So it's going to be, we'll have a square root of 2. And it's going to be in the negative direction. So this guy, if we're looking at frame B, it's in the negative frame direction for J. So we'll have negative square root of 2. And then we'd have JAB is equal to, and again, I'll put the 1/2 out front. JA, again, it's in the positive direction of of I in frame B, so we'd say that this is the square root of 2. And it's also in the positive direction of J for frame B. So we'll say this is the square root of 2. Okay. So we now have defined our I-axis in terms of frame A in coordinates for frame B. So we're going to directly write down our rotation matrix from these vectors. So we can call this a direction cosine matrix because we're just looking at the direction of where these axes are in the other frame. So this nice direction cosine matrix, we'll see where cosine pops up here in just a second. But we're going to define our notation, A to B. This is going to be the rotation matrix from frame A to frame B. So we're defining that rotation from frame A to frame B. And we just simply write it down. It's going to be, we have frame A's I vector written in frame B, and frame A's J vector written in frame B. So we have just this I and J of frame A, but written in frame B coordinates. So in this case, we could write this down, pull out the 1/2, and we'll do a square root of 2. We already did this, minus square root of 2, square root of 2, square root of 2. Okay. Another way we could have written this, as r of some theta. This is just the cosine of theta, negative sine theta. Sorry, I kind of ran out of room. Sine theta and cosine of theta. Okay, so note that this is actually just backwards from how some other texts, like I put here Lavelle in his planning algorithms text, defines the rotation matrix with the negative in the upper right. So they would have defined it, instead of having the negative down here, would have been up there. Okay, this is just for the fact, the reason we get the negative down below is because we've defined the angle from A to B. In Lavelle, it's defined from B to A. So really the same thing, just a note to keep in mind. So you'll see rotation matrices defined with the negative in one spot versus the other. You just have to keep in mind that that's because we've just defined how the angle differently, whether we're going from one frame to the other or vice versa. Okay, so this is really cool. So we have two ways of expressing the rotation matrix. One is a straight up direct cosine matrix form, and one is in terms of the angle, directly in terms of the angle. So they're equivalent, but the direction cosine just helps you understand that what we're really doing with that rotation matrix is we're just taking, right, the direction of the x-axis and the direction of the y-axis in one frame and expressing it in terms of the other frame. And that'll help us transform between one thing and another. Okay, so let's do a simple example. I'm going to define the point P right here. And if I were to find the point in the B frame, it's pretty easy, right? I'm going to just say that this is 2i, 2i sub B in the B frame, which is just equal to 2, 0. And like before, this is simple enough since we're using just a rotation of pi-4ths. We can write this in the A frame as equal to, if we're to look at this point, we know because this is an angle of pi-4ths, And we'll end up just getting the square root of 2, square root of 2. Oh, and I should have put that as a vector matrix, vector, column vector. So let's see if we can get the same thing out. Okay, so we'll say that we've defined our rotation. Oops. Oh, man. I missed a B there. Okay. We've defined it. We know what point A, we know what point P is in the A frame. It's just the square root of 2 over the square root of 2 in both coordinates. So we have P in the A frame. It's just equal to square root of 2, square root of 2. Okay, so let's make sure that our transform works. So in this case, we would write down that P in frame B. What we do is we just multiply the rotation matrix, A to B, times PA. So we have this kind of a cancellation. So we have expressed it in frame A, and that's up top and down low, and then we're left with the superscript B. Okay, so that's how we're going to write down our transform between frame A and frame B. Well, let's just work it out. So we're going to end up getting, let's just write everything out here, square root of 2 over 2 times, and I'm just writing our rotation matrix. We have 1, 1, minus 1, 1, times PA, which was the square root of 2 times, we had 1, 1. Okay. So in this case, we're going to end up getting, we have square root of 2 times square root of 2 is equal to 2 over 2 times 1, 1, minus 1, 1. And multiply that by 1, 1. And we end up getting, we have, so this is just a unit, so we have 1 plus 1, and then we have, not all over. Then our second element is negative 1 plus 1. This is equal to 0. Okay, excellent. So that was perfect. So if we were to transform it back, the easiest way to get our reverse transform is to just look at this formulation. So if RAB, we have that RAB is equal to the rotation matrix from using our theta, right? In this case, we did pi fourths. Well, to get it back, we're going to say that RBA is equal to the rotation matrix, and we'd just do the negative angle there. So we'd be going that direction. So we'd say of negative pi fourths. Okay, one simple thing to note is that if we do the cosine of theta, of minus theta, that's just still going to be equal to the cosine of theta. It's the exact same thing. So sine of negative theta, since it's an odd function, we'll get the negative sine of theta. So that's really nice property. So now note that we're just putting in this minus sign right here. So we can just, what we're going to do is our cosine terms, our diagonal terms are going to stay the same. Right? So our diagonal terms will stay the same, and we're just going to flip the sign on our off diagonal terms. So we'll end up getting, so if we had our, and I don't know why I put it out front, didn't put it out front, we have square root of 2 over 2. Diagonal terms stay the same, still going to be 1, 1, but instead of the negative being in the lower left, it's going to be up in the upper right. Okay, so let's transform this point, right, which was just equal to P, let's see, in the B frame. Let's transform it back to the A frame, and hopefully this thing works out, right? So we just do that PA will then be equal to our RBA times PB. Well, we know that this is our RBA, so this is equal to square root of 2 over 2 times 1 minus 1, 1, 1. And then we have our 2, 0. Okay. So doing the math, we have, square root of 2 over 2. We're going to end up getting 2 there plus 0. And then we're going to get a 2 there plus 0. So it is equal to, these 2's are going to cancel out with that 2. We're just going to have a square root of 2 and square root of 2, which is what we had originally. Okay, so we can take it, we can transform it one way and then transform it back. Now, one thing that we noticed, right, is all we did was we changed the sign locations when we were doing the reverse transform. And what we can see here is that our RAB is just equal to the transpose of RBA, which is fantastic. So that's a really nice property. If we want to get the reverse transform, all we do is we take the transpose. That actually holds for both 2 dimensions and 3 dimensions. Okay, so we've got a nice little example there. So we could have, let's now look at a different problem, right? What we want to do is see what's the transformation matrix that takes us from one frame to another and then back again to the initial frame, right? So to write that down is, I want to say that, we have that PB is just equal to the RAB times PA, right? And we have that PA is equal to RBA times PB. So we have these two relationships. Let's just substitute one in for the other. So let's say that we have PB. Let's put it into this equation. So we have PA is equal to RBA times, now we have RAB PA. So again, this is just PB. Okay, so now we have that PA. So let's just write it nicely. PA is equal to RBA times RAB times PA. Well, we better be left with the identity matrix. So let's use the angle form, because this is nice. It parameterizes our rotation matrix in terms of just a single angle. So what we're going to do here is we'll just say that this is equal to cosine of theta, sine of theta, negative sine theta, and cosine of theta. And then we would just be flipping this diagonal for the other one. So we have this is cosine of theta, still cosine of theta. Then we have negative sine theta, and we have sine theta. Okay, and if you work this out, you'll end up getting, this is just 1, 0, 0, 1. So just do this matrix multiplication, use our trig identity, right, that cosine squared of theta plus sine squared of theta is equal to 1, and things work out rather nicely. Okay, so this is really important. So the transform from any frame to itself is equal to the identity. This is another property that holds for both 2 dimensions and 3 dimensions. And let's see. Since we have that one times another, so there's another slight property we get from this. Since we have that RBA times RAB is equal to the identity, well, that means that one matrix is the inverse of the other. So because if you have two matrices, M times N is equal to the identity, that means that M is the inverse, if they're both square matrices, sorry, inverse of N, and N is the inverse of M. Again, these are square. Okay, for square matrices, there we go. We have that nice little property. So we have two square matrices multiplied together and they're equal to the identity. Well, that just means that RBA inverse is equal to RAB. And we already talked about the fact that this was equal to the transpose of RBA, right? So we already talked about that this is equal to its transpose. So that's really cool property then, that the inverse of a rotation matrix is equal to its transpose. Makes taking inverses really easy. So we can just transpose the rotation matrix and we get its inverse. Okay, now I'm going to do one note on this idea of rotation matrices. You'll see two different types of rotation matrices defined in the literature. One is a fixed point and a rotating frame, what we just did. So i.e. fixed point meaning, we use the example of Chicago. Chicago doesn't move. The rotating frame does, so we could, our frame of reference does. Okay, so Chicago doesn't move, our frame of reference does rotate around. So that's what this passive is. So in this case, we have our two frames, right? But our point P is fixed. Okay, so that's this passive rotation, that that we can move our frames around all we want, but we're not actually changing the points themselves. So another type of rotation is active rotation. So in this case, we actually have a fixed frame. We only have one frame of reference. So what we're going to do is we're going to change the point. So in this case, we're going to change the location of the point. So say we have a point P defined here, and we could essentially define a new frame that we're going to, if this vector points directly at point P, we call that the angle to get to it. Oh, sorry. This, if we want to move that rotation, if we want to move P by a different angle, right? So say we wanted to move it to be down here, then we can define a rotation matrix that'll move that point down. So now these are actually two different points. Okay. And so one is actually just the negative rotation matrix of the, not negative rotation matrix, but the rotation of the negative angle. So say we had a r of theta here, we would actually define our r of negative theta here. But the idea again is we're just rotating from one frame. The second one is that we're actually moving the point. The top one is we're just changing our frame of reference. Okay, so now we've talked about a single rotation. Now let's chat about two separate rotations. So now we have frame A as before, frame B, and we're going to have frame C. So red is A, blue, so this is going to be our, this would be our I in the A frame, our I in the B frame, and this guy is going to be our I in the C frame. So we have three different frames of reference, and we can relate them by two different angles. So say we have the angle from from A to B, let's call that theta 1, and this guy from B to C, we'll call this theta 2. So we rotate once, and then we rotate our frame again. Okay, so we have that our total rotation, oops, I should just write this here. Our total rotation is that we have r of theta. Oh, I didn't mean to write the total rotation is just adding over the two rotations. So we have theta 1 plus theta 2. So in this case, we would just write our r of theta is equal to r of theta 1 plus theta 2. And we can write this down in two different ways, right? We could either say that this is our cosine of theta 1 plus theta 2. We have our sine theta 1 plus theta 2. We have negative sine theta 1 plus theta 2. And cosine of theta 1 plus theta 2. Well, that's also going to be equal to the rotation about theta 1 times the rotation about theta 2. And it would actually equal to the rotation of theta 2 times the rotation of theta 1. So in other words, for the two-dimensional case, we have that our rotations are commutative. So we have a commutative rotation for the two-dimensional rotations. So in reality, 2D rotations are really easy to work with, right? Because we only have to worry about a single rotation matrix. But if we do it step by step, kind of like I showed up here, then we'll end up getting something that can work a little bit better for 3D. Because rotations are commutative, and this I would need to put in red for 2D. And this is only for 2D. For 3 dimensions, they're not. That's not completely true, but it's because that when we rotate in 2 dimensions, we're rotating about a single axis. If we rotate in 3 dimensions about a single axis, then those rotation matrices are also commutable. Okay, so let's do it step by step. So in this case, we could say that if we're given a point, right, and we have our point P, and say we know our point P in frame A, right? Well, we could write point P, say this is known. Point P in frame B would just be equal to, and would say this is a rotation from A to B times point PA, right? So nothing new there, which in our case was equal to r theta 1 times PA. Okay, and then we have also that point C, the same point P in frame C, is equal to RBC times PB, right? Which is just equal to R theta 2 times PB. So nothing too crazy there. We do one rotation at a time. Well, now if we plug in our value for PB, right? Oh, and I'm actually going to use this value for PB to make it more general. We then have that we'll go from BC, and then we'll do A, B, P, A. So we can now chain together these rotation matrices in a very methodical way. So again, given PA, and in effect, we were given R BC and RAB, right? So by being given theta 1 and theta 2, we know that we can now express point A in frame C really easily. So here's our point in frame C. And we could do it again. So if we have, if we know that our C to D is known, then again, we could just continue to chain it together, right? We'd say that P in frame D is equal to CD. We'll go from B to C. We'll go from A to B. And this, we are now multiplying on the end by PA. So we can just chain these rotation matrices together, which is really nice. So while we can write our rotation, this guy, I should have said that this was equal to RAC, right? We can write our rotation from A to C really easily in 2 dimensions just by adding the angles. Well, we can do it in a very methodical fashion, and this translates into 3 dimensions as well. Okay, so quick fact, right? 2D rotation matrices are commutative, 3D are not. So, and we can take a look at that again here in just a second. 2D rotation matrices belong to a group called special orthogonal group of 2 dimensions. So this is typically written, oh, looks like we're missing a closed parenthesis. This is typically written as SO2. Right, so our rotation matrix, if it's our 2 by 2 rotation matrix, is in the set SO2. So we're not going to go into too much, we're not go to any detail really, except for the fact that it's a set of matrices such that R inverse is equal to R transpose, which we've already seen. And we have the determinant of R is equal to 1. So that's our special orthogonal group. All right, now let's jump into 3 dimensions. Okay, so we have, it gets a little bit more complicated to just draw it out, right? So we have our, so this is, say this is I, B, J, B, and K, B. And we have our frame A, which we'll do in red like normal. Say that this is frame I, A, J, A, and say that this is also K, A. So we end up, we end up having 2 frames of reference. Okay, and maybe I'll do this more generically. Say that our KA is over here. Okay, so now we have this other frame, which is great. So now we have 2 frames of reference. Again, all we've been doing is 2 frames of reference. We can still just write our direction cosine matrix just as before. So let's go back to that when we first introduced the 2 dimensions. We just wrote that the rotation matrix from A to B was just equal to the I and J in frame A, of frame A represented in frame B. And we can just directly write out our rotation matrix like that. We can do a similar thing for our 3-dimensional Okay, so what we would do is we just say that R from A to B is equal to IA, JA, and KA, all written in frame B. So expressing each one of those vectors in frame B. Where now, since we're in 3 dimensions, we write our elementary vectors as such. We have IAA, would just be 1, 0, 0. We have JAA would be equal to 0, 1, 0. So basically the same as before. And now we have this new KAA is equal to 0, 0, 1. Okay, but that's if they're expressed in the exact same frame. Unlike the 2-dimensional scenario where we had 1 rotation, in the 3 dimensions, we're going to talk about 3 different parameters. So for elementary direction cosine matrices, what we're gonna end up introducing 3 basic rotation matrices, and we can combine them together to form any 3-dimensional rotation matrix. So if you're to look in various texts, they'll describe these different ways. All we're going to do is use the right-hand rule. So given a vector, we're going to grab it with the right hand, and we're going to do a positive rotation if we're grabbing it and moving, basically bringing your hand into your body. All right, so that's going to be a positive rotation. So we're going to do positive right-hand rotations about an axis. Okay, so for the 3D, there's 3 elementary rotation matrices. So the very first one is, we'll write it x, and we're going to write this in terms of a variable phi, and we'll get at that in a future lecture. But basically, if we took our, we'll show it in a picture. So what we're going to do is we're going to say that we have r, and we could call this x, and we'll parameterize it by phi. We're just going to be equal to 1, 0, 0, 0, we'll have cosine of phi, sine of phi, 0, negative sine of phi, cosine of phi. Okay, excellent. So if we jump back to our coordinate frame, so we have phi defines our rotation about x-axis, and remember x-axis is red. So if we come here, if we do a positive rotation, it's just moving the other axes around there. So we're just rotating our axes. So we're rotating the green and the blue, which correspond to our y and z, just about that x-axis. Okay. Oops. So that's our x rotation. There we go. Okay. So now we'll jump over. If I can get it, we'll jump over and we'll write down our y rotation. And our y, we're going to parameterize in terms of theta. We'll say that, oh, that was a really ugly theta. So we'll write our r of y in terms of theta is equal to, and so if you'll notice here, we're going to actually develop a pattern. So for the x rotation matrix, we had a 1 in the x component, the 1, 1 component. In the y, we're going to have on the second row, we'll have a 0, 1, 0, and we'll have it like that. So we'll have 1s and 0s, similarly to the x. But then we'll have a cosine on the off diagonal, so cosine of theta, cosine of theta. And now we're going to put a negative sine of theta up top and a sine of theta down below. Okay. Before we jump back to the GUI, let's let's do our z. And our z we're going to parameterize in terms of psi. So we'll say that our z of psi is equal to, and we're going to have our 1 down in the z location. We'll have our cosine of psi, and we're going to have our negative sign again in the lower component. So that's going to be our elementary z rotation matrix. So again, let's go back to the GUI here. So theta, again, remember, is about that y-axis, that green axis. So if we're doing a rotation about the green axis, right, positive rotation, now we'll go to negative rotation. It's basically just changing. We're grabbing that axis and moving things around. Okay, we'll get it close enough to 0. And then we'll do a rotation about our z-axis, right? Our z-axis, again, is positive rotation. If we were to grab our hand on that z-axis and move it around in a positive direction, that was positive, and this is now a negative rotation about the z-axis. So we have that. These nice elementary rotation matrices are just at one axis at a time. Now, when we talked about 2 dimensions being commutative and 3 dimensions being not commutative, realistically, 3 dimensions can be commutative as well if you do it about the same axis, right? So I can do, right, a pi fourths plus a pi fourths, and we get a rotation of pi. So if we keep it about the same axis, we can do as many rotations as we want, and it will actually be commutative. It's when we rotate it about one and we rotate it about another, now our rotations end up not being commutative. Okay. So, I lost my pen. Excellent. So we can come in and we can now define any rotation, any 3-dimensional rotation, or 3D rotation, yeah, can be expressed using these elementary direction cosine matrices. So, for example, we have an x, y, z rotation. We call this our roll, pitch, and yaw. So this is an Euler rotation matrix. And what we're going to do is we'll just do our rotation that's about our x, right? Our x rotation, our y rotation, and our z rotation. So just like we showed on the previous slide. And we'll get an aggregate right here. So this is our aggregate rotation matrix with these 3 elements where we have these 3 angles. And often we'll just write this, because we can do it in any of these 3 angles, we'll write this we'll do that capital theta notation, and we'll just say that this is our rotation matrix is a function of our attitude. Okay, so this is really cool. So now all we've done is we've combined our x, y, and z rotations, and we can get to any attitude that we want. Now, one thing to be careful about, there are many different types of Euler formulations. Sometimes there'll be x, y, x. You can organize these rotation matrices in different order. And remember that for 3D, if we switch the order of these matrices, it's not commutative. And so be very careful. Be very careful to know that what type of Euler transform you're talking about. Okay, so if we look at this notation here, right, where this was equal to Rx times Ry times Rz PV, right? What we need to look at is what rotation. The question here is which of these rotations is performed first. And so the thing to note is that we do that rotation first. That'll actually get us, this will then be equal to Rx times Ry, and this would be our P. And remember, we're now in our vehicle 1 frame. And then we'd do this rotation second, it would be Rx, and then this would just be our P, and now would be in our vehicle 2 frame. And then we go from our vehicle 2 frame to our body frame. So just keep that in mind. We're basically just doing one rotation at a time. Okay, so a few important properties we have is that rotations are not commutative for 3D. It's because anytime you start rotating about a different axis, you cannot switch the order arbitrarily of your matrices and get the same result. So 3D rotations are not commutative. This is something to keep in mind. 3D rotations do belong to a group very similar to two-dimensional rotations. This group called SO3, Special Orthogonal Group of 3 Dimensions. Okay, we won't use that too much right now, but it is important to note that when somebody talks about SO3, again, it's just that R inverse is equal to R, and the determinant of R, it's the special orthogonal group, we're going to use 1. Okay, the 3D inverse is the same as the 2D inverse, meaning that we have that RBA is inverse is equal to RAB, which is equal to RBA transpose. So we still have that same property. We can also chain 3-dimensional rotations in the same way that we did 2-dimensional rotations. So given RAB, RBC, RCD, we can write that P in frame D is just going to be equal to RCD, RBC times RAB times PA. Okay, so we can still chain together those 3-dimensional rotations. Another thing that we mentioned is take extreme care when you're given Euler angles. So there's 12 different possible combinations, and they're all called Euler angles. So be really careful, make sure you understand that you're only use this version of the rotation matrix when you have X, Y, and Z rotations. Okay, so the two big differences between 2D and 3D rotations is that 2D has 1 angle, 1 degree of freedom, and 3D has 3 degrees of freedom. So we have to define 3 parameters to get our 3-dimensional rotation matrix. Another thing to note is that 3D is not commutative. So I've said it a whole bunch of times, but we need to make sure that you know that Rx times Ry times Rz is not going to be equal to, not necessarily going to be equal to Rz times Rx times Ry, right? So that's not commutative. Okay, so that finishes up 3D rotations. Now let's do our 4th transform. We're going to do 3D rotations and translations, right? And that's what we started off the lecture with when we looked at our GUI. We can have translations. Whoops, let's not get it too far. Translations and rotations, right? So we have it combined together. So again, the point is could stay fixed, but the axes they're no longer parallel because we've done a rotation, and they're no longer co-located because we've done a translation. Okay, so moving back, so now we have this 4th transform, and for now we're gonna take the easy way out, because for this class we're really not going to be playing with this very much. But let's talk about it just a little bit. we have this group, we say this is SE3. So it's now, instead of the special orthogonal group, we call this the special Euclidean group of 3 dimensions. And it's just equal to the set of all P and R such that P is in R3. So we have basically a 3D position or 3D vector. And our R matrix is in SO3. And you could do the same thing for 2 dimensions. It's going to be SO2 instead of SO3. Or, yeah, SO2 instead of SO3. And the result would be the special Euclidean group of 2 dimensions. So say we have a point and we want to rotate it and translate it. So now we have frame A again, and we have frame B, right? And say that we have this point P, easy to express in frame A. How do we get it to frame B? So the goal is, again, we have P A, oh, sorry. We have PA, and we want PB. Okay, so it's actually not too difficult. We're just going to combine what we have already done, right? So we're going to define this vector. Again, this vector V, and it's going from A to B, and we're going to define it in frame A, right? Sorry, I actually started to do this backwards. Let's say that we have a frame and point in frame B. So let's draw this so it's a little bit easier to say that, hey, yeah, no, so we know point P in frame B, and we want to know it in frame A. So we're going to end up defining point P in an intermediary frame. So let's first rotate it. And we're going to rotate it to a frame that's parallel to frame A. To a frame parallel to frame A. Okay, so we want to rotate it to a frame that's parallel to frame A. So if we were to draw this over here, right, we'd end up having this new frame. And this is just going to be our intermediary. It's an intermediary frame where we haven't added the rotation. But since vectors, when we translate them, do pure translation, we saw that they were the same. We can actually just say that we're still going to do the rotation from frame B to A first. So we end up doing our, oops, and then, oops, I meant to have that in blue. And our second thing we're going to do is we're going to add in the difference vector. Okay, so then if we said that we have point P, frame A, is going to be R, oops, yeah, R from B to A of point B, plus we have VAB point in frame A. So we have just our translation right here, defined in our frame A translation. So it's a translation from one frame origin to another, defined in frame A, and we have our rotation. Okay, so we just do our rotation first, and then we translate it. Okay, so that'll give us our full transform. So we can transform a a point or a vector, we can transform that point from one frame to another, and that frame can have different origins, and the axes do not have to be parallel. And I want to quickly touch on these frames that we have up at the very beginning. So the body frame is the frame where we have the axes are aligned with our aircraft. So what we would typically do is, if we're going to go from our body frame to our inertial frame, we rotate it. We go from our body to our vehicle through these chains of rotations, and then we add in that inertial frame to get to, or add in V to get to our inertial frame. So let me write that down mathematically. For the UAV case, we're typically going to do our PB, our body frame, to our vehicle frame. We'll jump into that more in the future lecture. So in this case, we would say that PV is equal to the rotation from our body to our vehicle times PB. And then we're going to do our inertial, or our PV to our inertial frame. All right, so in this case, our PI is equal to V I to V as expressed in the I frame times P, plus PV, which you can see is just exactly what we'd written before. Plus we have our rotation from B to V, P, B. So that's how we're going to do our three-dimensional rotation and translation. Okay, so just in summary, we have defined different frames of reference where we can talk about points and vectors in an easier fashion. We discussed three basic transforms. We have the pure translation, we have a 2D rotation, a 3D rotation, and I don't know why I left off. We have our 3D translation and rotation, and it really just puts the two together. And to also keep in mind that we discussed two different types of rotation. Passive being that we're keeping the point at the same spot, active meaning we're actually trying to move the point around. We'll always be doing passive in this class. Okay, so on our pure translation, we're going to have 1 degree of freedom for each dimension, right? In our 2D rotation, we actually only have 1 degree of freedom. In our 3D rotation, we have 3 degrees of freedom. So when we do 3D translation and rotation, that's going to be 6 degrees of freedom. So 3 for translation and 3 for rotation. Thing to note is that our inverse is equal to our transpose. That's really helpful for our rotation matrices. That goes for both 2D and 3D. And keep in mind that that 2D rotations, we can consider them commutative, but 3D rotations are definitely not commutative. Okay, and we also talked about the elementary rotations that we can use. Excellent. Have a fantastic day.